Hey y'all, today we're going to be looking at the concept of half-life. Half-life takes the integrated rate laws that we learned about in the last video, and it applies them to a very specific function. That is the amount of time it takes for half of your reactant to be reacted or be gone. So if we think about half-life, one of the contexts that you'll most often hear about it is with regards to radioactive decay. We talk about the half-life of radioactive elements a lot. And in fact, in this course, we will talk about that a little bit. But the thing to know is that half-life doesn't just apply to radioactive elements. It applies to any chemical reaction. The half-life would be the amount of time it takes for half of your reactant to have been used. So we're going to go ahead and apply half-life using our integrated rate laws. And I'm going to show you how we're going to actually take our integrated rate laws and manipulate them to be able to predict half-life and be able to use half-life as a quick and kind of dirty method to be able to figure out whether a reactant is zero, first, or second order without having to do any math whatsoever. Let's get started with zero order rate laws. Now, the integrated rate law for a zero order reaction, remember, is the concentration of A at time t minus the initial concentration is equal to negative kT. I'm going to solve this like a system of equations because remember, half-life represents the time at which the concentration is half of where it started. So that means that A at time t is equal to 1/2 the initial concentration. I'm going to substitute in, and I'm going to solve for half-life, which is now t of 1/2, and that's the t we're actually looking for. So what does this tell us? Well, mathematically, you don't need to really be able to use this all that often, okay? But it tells us a lot in terms of graphs. What it tells me is that if I'm looking at a graph of a reaction, and I'm looking at a reactant, if the half-life becomes shorter over time, then this is going to look as a zero order reaction. So in other words, we look at this concentration being on the top. The lower the concentration gets, the shorter the half-life becomes. And there's a trick to this. See, that initial concentration, it doesn't actually matter that it's at time zero. You can have an initial concentration at time zero and then just move the goalposts. Say, all right, well, maybe my initial was at 5 seconds or 10 seconds or 30 seconds or 6 hours. Because it doesn't matter where you start that initial. All that it matters is that as time goes on, each half-life becomes shorter and shorter and shorter. That's representative of a zero order reaction. Let's take a look at first order now. First order reactions have the integrated rate law of natural log of A at time t minus the natural log of the initial concentration and that's equal to negative kT. Now, we're going to do the same thing here. We're going to solve it as a system of equations, okay? So the way I'm going to do that is by saying that the A at time t is equal to 1/2 the initial concentration. Now, if we look at this complicated equation, one thing you might notice, hopefully, is that one of our log rules plays a role. Now, if you remember the log rule where it's subtracting logs, the natural log of x minus the natural log of y is equal to the natural log of x divided by y, which means we can actually do that here. So what I'm going to do is I'm going to combine those two log functions together, which results in the natural log of 1/2 A naught over A naught, the initial concentration. Now you'll notice that A sub 0 divided by A sub 0 cancels out. So we're left with the natural log of 1/2 is equal to negative kT. The natural log of 1/2 is just a number. The number is negative 0.693. So what that tells us is that negative kT is equal to negative 0.693. So if we're solving for half-life, what we're going to do is simply divide by negative k, which gives us this equation here. Half-life is equal to 0.693 divided by k. Now, the most important thing to recognize about this is that concentration is not there. The concentration had canceled out. So in a first order reaction, the concentration plays no role in determining the half-life. That's really important. So if I look at any two time points where the concentration has been cut in half, those times are going to be equidistant apart. The half-life does not change over time of a first order reaction. This is most applicable when we're talking about radioactivity. The radioactivity of atoms is a first order reaction. So if I'm looking at the radioactive decay of uranium, that's a reaction that decays with first order. That means that the half-life never changes. And it actually can be really helpful. In the case of radiocarbon dating, for example, we're using a radioactive isotope of carbon to be able to predict how old something is. Well, in order to do that, it needs to decay at a constant rate. So we can use radiocarbon dating because first order reactions are independent of their concentrations. Now let's look at second order. Remember, again, we're going to do the same thing we've done in the past, which is substitute in for the half-life, which is A at time t is half of the initial. Now, if we simplify this, it's 2 over initial concentration. Now, recognize that we have a common denominator here, so we can just subtract. That means KT is equal to 1 over the initial concentration. It means if we solve for half-life, all right, T of 1/2, then we're going to divide both sides by K. So the half-life equation for a second order reaction, the concentration's in the denominator. So as concentration goes down, the half-life actually gets longer. So now hopefully you can recognize how we can determine between a zero order, first order, and second order just based off of their half-lives. If we look at a graph, if the half-life does not change between two times where the concentration has been cut in half, and remember, half-life is a time. So if I look at this graph, for example, and the concentration between times 0 and 10 gets cut in half, and then it's the exact same amount of time between 10 and 20 where it gets cut in half again, so it's now 1/4 of where it was, that tells me it's first order with respect to that reactant. If the half-life gets longer, it's second order with respect to that reactant. If the half-life gets shorter, it's zero order with respect to that reactant. So what we can do is take a graph, look at successive half-lives, and if the second half-life is not the same as the first, determine if it's greater than the first or less than the first. And with that information, we can now determine if it's zero, first, or second order with respect to that reactant. Remember that the half-lives of radioactive isotopes or radioactivity is always going to be first order. They might not even tell you it's first order because you have to know that it's first order. So that wraps up today's video. Today, we manipulated our integrated rate laws and utilized them to be able to determine the half-lives of zero, first, and second order reactions. Now, you're going to be given the half-life equation for first order only. You will not be given the equations for zero or second order. Okay? You're not going to be asked to calculate those either. But it is important to know how concentration causes changes in half-life for each of the zero, first, or second order reactions, because it's going to allow us to use graphs to recognize whether something is, in fact, zero order, first order, or second order. I hope you enjoyed this video, and I'll see you in the next one.